All right, welcome to day 5. Notice on tonight's homework, there's one question, number 6, that you are going to hand in for a grade. So, I am going to have 2 spots for you to upload things on Schoology. There's going to be a spot just for the general homework problems, and then also I'll have a spot for, I'll call it like the day 5 graded problem or something like that. So if you could upload a picture of just that problem there, and we'll do a couple that are going to be similar to what you will do in that problem in the video today. Okay, there's your homework answers, so you can pause it so that you can check each of those answers and then unpause it when you're done checking them. And then I'll pause for a moment on each of the worked out solutions so that you can check those. So anything from the worked out homework that you're unsure of, please post your questions in the content discussion board on Schoology, and myself or any of you can respond and answer to those questions. So first off, we're going to be using today our different sigma rules. So we need to be comfortable with those from day 3. So if you look at the day 3 in the notes, the ones that are going to be important for us are first our constant formula. We'll also need our I to the first formula. And I have it on there as n over 2 times n plus 1. You could also think of it as n times n plus 1 all over 2. Either of those are fine. You've got your summation from I equals 1 to n of I squared. So that's n times n plus 1 times 2n plus 1 all over 6. And then the last one, I equals 1 to n of I cubed. Now on our sheet, we initially had it as n squared times n plus 1 squared over 4. Or recognize that that's just our I to the first one, n times n plus 1 over 2 all squared. So either way that you want to think of it for the I cubed one. But we'll be using those today, and you'll be using those on the graded homework problem tonight as well. So we're on the day 5 notes, and we'll be starting with this picture. So it should say 2-5, BC 2-5 on the top. So when we do an integral, a definite integral, I should say. Definite meaning it's got the values on the integral. Our answer is a directed area, meaning it's telling us the net change of the area above or below the x-axis. Any area above the x-axis is considered positive area. Any area below the x-axis is considered negative area. So let's say we want to find the exact value of our integral from -2 to 4 of 2x minus 4. So the directions say we're going to use this with geometric formulas. If you see that, that basically means formulas we already know. So areas of rectangles, triangles, trapezoids, circles. So there should be some formulas that we know that we could do that. So this is a line that has a y-intercept of -4 and a slope of 2. So it should look something like that when we're going from -2 to 4. Well, we're finding the area between the graph and the x-axis. On the left, we have a triangle that's below the x-axis, so that's considered negative area. To the right, we have one above the x-axis. Now, the x-intercept, the value that would make that equation 0 is just 2. So therefore, we have a base of 4 for this. And if you sub in negative 2 to our equation, we'll get negative 8. Or actually, let's have us just think of it 8 as 8, and we'll know it's got to be negative. So it's a minus area because it is under the x-axis, and we'll just do base times height divided by 2. Well, then the other part has a base of 2, and if you sub 4 into the equation, that's 8 minus 4, which is 4, so this height is 4. It's going to be positive area because it's above the x-axis, and we'll have 2 times 4 divided by 2. So this is really 32 divided by 2, so in other words negative 16. 8 divided by 2, so in other words 4, so we end up getting negative 12. The fact that we got a negative 12 to our answer for this integral means there must be more area under the x-axis than there is above the x-axis. Now our next one, we got square root of 16 minus x squared. Imagine if that was equal to y. If you squared both sides and move the x squared over, that'd be x squared plus y squared equals 16. So we know from that, hopefully, that we're working with a circle centered at the origin with a radius of 4. But if you go to get y by itself, so if we kind of worked upwards this way, we would need a plus and minus in front of that radical to be the entire circle. So the fact that we only have the plus in front of the radical means we're working with only the top half of the circle. And it's going from negative 4 to 4. So a semicircle, we just have 1/2 pi r squared. In this case, our r is just 4, so 16 times 1/2 is 8, so we just get 8 pi for our area. Notice it's above the x-axis, that's why it was positive. Okay, so for this next one, we've got an absolute value graph that's shifted up 3. So there's our graph there. So this value is 3, we know. And we're going negative 4 to 0. So notice we're only doing this part to the left of the y-axis. Well, you can do this one of two ways. We've got a trapezoid. Your trapezoid formula is 1/2 height times base 1 plus base 2. Or you could split it into a triangle and a rectangle. We're going to go ahead and do the trapezoid. This trapezoid's turned on its side, so the height is really the 4. Base 1, one of them we could say is 3. And the other one, well, if you sub negative 4 in for x here, absolute value is 4. 4 plus 3 is 7, so we'll get 7 for the other height. So that'll be 10 times 4 times 1/2. So that's really just 10 times 2, so we get 20 for our exact area. And our last geometric one we'll do, let's say we had sine from negative pi to pi. Well, these sections should be identical. We don't know necessarily the exact number. We know this negative number should match that positive number. So when you add them together, this should just give us 0. So if you get an integral whose value is 0, that means the area above the x-axis and the area below the x-axis on that interval must be equal. Okay, so now on to a little bit more challenging stuff. So definite integrals can be approximated by Riemann sums. So these integrals, the exact values of the integrals we were doing here, it's great if it's a shape that we can do an actual geometric formula for. But we might not always be able to do that. So we saw yesterday that we could approximate the area under with Riemann sums, those rectangles. Well, our estimate got better with the Riemann sums if we had a larger number of rectangles, because that made the width of the rectangle, the intervals, smaller. When the intervals were smaller, there was less error. Well, imagine you make those number of rectangles go to infinity. That's our n here, n going to infinity. Well, if the numbers of rectangles approaches infinity, they're getting infinitely thin, and it's approaching the exact area under the curve. So the limit of your Riemann sums as your number of rectangles becomes enormous will equal the exact area under the curve. And that's what this is saying. Exact area under the curve is equal to, as your number of rectangles go to infinity, as you add up those Riemann sums. This is really the base of each rectangle, and that's really the height, because it's the y value. And then the summation is adding up all those base times heights, and we're letting our number of rectangles become huge. So it's kind of complicated looking, but we're going to show you how we can use those I formulas from day 3 to actually find the exact value of an integral. So we're going to work with the integral from 0 to 2 of x cubed. So we have a picture of it there. So the first thing we want to do is find delta x, that width of each interval. Well, to do that, we always do b minus a over n. So in our case, we have 2 minus 0 over n, which would just be 2 over n. So the area of an ith rectangle. So we say ith rectangle is just some random rectangle in the interval. Well, the base of every rectangle is going to be 2 over n. So we got to do a base times a height. So we'll have 2 over n times some height. Well, the height is found by subbing into x cubed. So we're going to have something cubed. We just need to somehow represent what's a random x value that we're subbing in. Well, they're saying upper sums and limits, meaning we're going to do the right-hand endpoints of our intervals for our reference points. So let's list out some intervals. In the first interval, we're starting at 0, and we would add each time our width. So say our width was a half, we would do 0 to a half, and then a half to 1, and then 1 to 1.5. So here, we're going to add on this 2 over n. And for right now, I'm going to write it as 0 plus 2 over n. Okay, we'll eventually drop to 0, but just so you can see how that 0 carries through. So the second interval will go from 0 to 2 over n, and we'll add on another 2 over n. So it'll be 0 plus, and we'll have 2 times 2 over n. Okay, because 2 over n plus 2 over n will give you 2 times 2 over n. Our third interval will go from 0 plus 2 times 2 over n, 2 over n, to 0 plus 3 times 2 over n. And so on. We got to imagine if we had a random ith rectangle, we want to know just what is the right-hand reference point, that right-hand x value. Well, notice what they have in common. They all have a 0 plus some number times 2 over n. Notice that number matches the interval that we're in. So in our ith rectangle, it should be 0 plus I times 2 over n. Well, 0 is not doing anything, so really that's just 2i over n. So our ith rectangle, the x value we would work with, is 2i over n in this case. If our start of our interval had been like 3, then we would have had 3 plus for each of those, and we would have had to sub in 3 plus 2i over n. But the 0 makes things a little easier. So now we'll just do our limit. We're going to have limit as n approaches infinity, sum I equals 1 to n. And now we'll just take this ith rectangle. So we have our base times each of our heights. And now the process begins to see if we can exactly evaluate this limit. So in our summation, to the right of the summation, we only need to keep the I things. because I is what we're subbing into. We're going to sub in 1 for I, 2 for I, technically, and so on. So anything else we can pull out front. Well, this here is the same as saying 8I cubed over n cubed. We need to leave the I cubed inside. But the 8 over n cubed and the 2 over n, we can pull out front to give us 16 over n to the fourth. And again, we could pull those out because they do not involve i's. Well, now this is where our formulas come into play. We're going to use our I cubed formula. So I have 16 over n to the fourth. Our I cubed formula, you can use either version of it, but one of it was n squared times n plus 1 squared all over 4. And what we're going to do, we're going to start neatening this up. We can divide a 4 out of each of these. So we have 4 there and 1 there. We can divide an n squared out of each of these, so that's gone. And this is just a 2 now. So if we rewrite, we have limit as n approaches infinity. This will now be 4 over n squared. And all that's left is the n plus 1 squared. So what I'm going to do is I'm going to FOIL that out. That's n squared plus 2n plus 1. We can distribute the 4 over n squared. So that would give us 4 plus, we would have 8n over n squared, so one of the n's wipes out. So we'd have 8 over n. And then plus 4 over n squared. Well, now we're ready to evaluate. As n goes to infinity, 4 is a constant, so it will stay 4. 8 divided by enormous numbers that keep getting bigger, that's going to get smaller and smaller, so that'll go to 0. 4 divided by enormous numbers, that will also go to 0. So therefore, this is just 4. So what we just determined is the exact area under the graph of x cubed from 0 to 2 is just 4. Now, if you're looking at that space there, it's kind of mind-boggling that it's such a nice number. And we'll see some patterns to make this process easier eventually, but for right now, this is the best that we can do. All right, we'll look at one more example of this. And again, this is the process you'll do on that graded problem. So we want to find our width, so we're going to do b minus a over n. So that would be 3 minus a negative 1 over n, or in other words, 4 over n. So our area of the ith rectangle is going to be 4 over n times our height. Well, the height is determined by the equation. Well, our equation this time is x squared, so we're going to have something squared. So let's list out our intervals. The first interval starts at negative 1 this time, and each time we're adding on 4 over n. So we'll have negative 1 plus 4 over n. The next interval is negative 1 plus 4 over n, and we'll add on another 4 over n. So we'll have negative 1 plus 2 times 4 over n. That was our second interval. Our third interval would be negative 1 plus 2 times 4 over n. We'll add on another 4 over n. So we'll have negative 1 plus 3 times 4 over n. And this process is just for us to help figure out what's the right-hand endpoint of that ith interval. We'll notice the right ends of the interval are always negative 1 plus whatever interval we're working with. So we have the ith here, times 4 over n. So in general, your right-hand endpoint that you'll sub into that equation is the starting value, the a. So it'll always be a plus I times delta x. Okay, that's the shortcut for it always. So our a value is negative 1 plus I times 4 over n. So I'm going to write it here as negative 1 plus 4i over n. So let's go ahead and we'll write our limit. We'll have limit as n approaches infinity. We'll have the sum of I equals 1 to n. We'll have 4 over n. We'll have minus 1 plus 4i over n all squared. So if we FOIL that out, FOILing it out, we're going to get a positive 1. We're going to get negative 8i over n when adding our inside and outside terms. And when you do the 4i over n times 4i over n, you're going to have 16i squared over n squared. And it's important to notice these i's are not representing the imaginary quantity coming from like a square root of negative 1. So let's distribute that 4 over n through. We will get 4 over n minus 32i over n squared plus 64i squared over n cubed. So we're going to write a separate summation for each of those fractions. We'll have limit as n approaches infinity. So this first thing, anything that doesn't have an I, we can pull out. So we can write this as 4n summation I equals 1 to n, and we'll leave a constant of 1. Minus anything that doesn't have an I, we can pull out. So we'll do 32 over n squared summation I equals 1 to n with the I left in there. And then we'll pull the 64 over n cubed out. Summation I equals 1 to n, we'll leave the I squared in there. Well, now we just have to do each of our formulas. So we've got limit n approaches infinity. We'll have 4 over n times. Our constant formula is just the constant times n. So we'll have 1 times n is just n. Here we'll have negative 32 over n squared. Our I formula is just n times n plus 1 over 2. So we'll have times n plus 1 over 2. And we'll have 64 over n cubed. Our I squared formula, that's the longest one. You got the n times n plus 1 times 2n plus 1 all over 6. So we don't have any summations anymore, which is nice. But we have some things we have to neaten up. So we have limit as n approaches infinity. 4n times n is just going to be 4. Here we can take a 2 out of each of these, so that's 16. We can take an n out of each of those. So essentially what we're going to do is we're going to distribute negative 16 over n through to the n plus 1. So negative 16 over n times n, the n's will wipe out, so we'll get negative 16. Negative 16 over n times 1 will give us minus 16 over n. Now this is going to be the messiest one. Let's first FOIL these two out. We'll get 2n squared. When we do the inside and outside, we'll get 2n and n. So in other words, we'll have 3n and then plus 1. And then distributing the n through, you'll have 2n cubed plus 3n squared plus n. And that's all going to be over 6. Well, then, if we divide them each by 6, this is going to be n cubed over 3 plus n squared over 2 plus n over 6. And we then have to distribute through the 64 over n cubed, and that's what we're going to fill in next in the equation. So 64 over n cubed times n cubed over 3, the n cubes will wipe out, and you just have 64 thirds. 64 over n cubed times n squared over 2, 2 of the n's will wipe out, so you still have an n on top, and then 64 over 2 is, or so you still have an n on bottom, sorry, and then 64 over 2 is 32. So we have 32 over n. And then distributed to the last thing, you'll have an n squared left on bottom, and 64 over 6 reduces to 32 thirds. So it's messy, but we're almost there. Because now we can just imagine n goes to infinity. Well, the constants stay, Anything with n's in the denominator, so that when the denominator gets huge, those are going to go to 0. So this will be 0. This is a constant. It stays. This will be 0, and this will be 0. So this is really minus 12 plus 64 thirds. In other words, this is minus 36 thirds plus 64 thirds. Or, oops, this is thirds, sorry. Or in other words, 28 thirds, which is the same as 8 and 2 thirds. No, I don't agree with that. Which is the same as 9 and 1/3, sorry. Okay, so let's talk about what we just found. We found that the exact area under x squared from -1 to 3 is exactly 28 thirds, that area underneath. You will be doing a process like this on number 6, the one graded one. If you get stuck on it, go back and watch these last 2 questions on the video. Have a great rest of your day, and remember to turn most of the homework problems in the regular assignment and the graded problem in the spot on Schoology specifically for that graded problem.